When sizing an electrical gutter that contains multiple conductors, the National Electrical Code, or NEC, requires adherence to Section 368.10a. This section addresses conductors with insulations of different thicknesses. According to Section 368.10a, when conductors of varying insulation thicknesses are installed within an enclosure or raceway, the minimum permissible fill, as determined by Table 1 of Chapter 9, must be calculated based on the conductor possessing the greatest insulation thickness present in the enclosure or raceway. Regarding conductor fill, NEC Table 1, Chapter 9, mandates that the fill for conduits and raceways be calculated using the conductor's cross-sectional area. The calculation is based on the number and size of the conductors. In this instance, there are three number 500 mil conductors. To determine the total area occupied by these conductors, multiply the cross-sectional area of a single number 500 mil conductor by 3. The cross-sectional area of a single number 500 mil conductor is 535 square millimeters, so 3 such conductors occupy 1605 square millimeters. There is also one number 3 conductor, which has a cross-sectional area of 120 square millimeters. Additionally, there is one number 8 conductor, possessing a cross-sectional area of 26 square millimeters. Summing these individual areas yields the total conductor area. This is calculated by adding 1605 square millimeters, 120 square millimeters, and 26 square millimeters, resulting in a total of 1751 square millimeters. Determining the gutter size necessitates adhering to NEC 368.10a, which stipulates using the largest conductor insulation thickness present. Given the conductor assortment, the number 500 mil conductor exhibits the greatest insulation thickness. Consulting NEC Table 4, Chapter 9 for number 500 mil cable provides guidance on the minimum gutter size. From that table, you can find that the minimum gutter size is 2.25 inches wide by 4 inches deep, or 57 mm by 102 mm. Regarding gutter length, the NEC does not specify a particular length, as it hinges on the specific application and installation scenario. Considering the distinction between a wireway and a pillbox, NEC 314.28 pertains to pillboxes, which serve to facilitate the pulling of conductors through a raceway or conduit. In this scenario, if the gutter is not employed as a pillbox, it need not be sized according to NEC 314.28. In conclusion, based on NEC 368.10a, the gutter intended for the specified conductor should measure at least 2.25 inches wide by 4 inches deep, or 57 mm by 102 mm. The ultimate gutter length is contingent upon the particular installation requirements. Now let us expand on these concepts for better understanding. The National Electrical Code, or NEC, is a comprehensive set of standards governing electrical installations in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC is adopted by many state and local jurisdictions and serves as the basis for electrical safety inspection. Article 368 of the NEC covers busways and cableways, but it also applies to wireways and auxiliary gutters. Wireways are sheet metal troughs used to protect and route electrical conductors. Auxiliary gutters are similar to wireways but are typically used to supplement wiring spaces at meter centers, distribution centers, switchgear, switchboards, and similar points. Section 368.10 of the NEC specifically addresses the fill requirements for wireways and auxiliary gutters. The fill requirements are designed to ensure that there is enough space within the wireway or gutter for the conductors to dissipate heat and to prevent overcrowding, which can lead to damage to the conductors or insulation. Section 368.10 states that where conductors of different insulation thicknesses are installed in an enclosure or raceway, the minimum allowable fill calculated in accordance with Table 1 of Chapter 9 shall be based on the conductor of the largest insulation thickness present in the enclosure or raceway. This means that when calculating the allowable fill for a wireway or gutter, you must use the dimensions of the conductor with the thickest insulation, even if there are other conductors with thinner insulation present. Chapter 9 of the NEC provides tables and examples for calculating conduit and raceway fill. Table 1 in Chapter 9 provides the dimensions of various conductors, including their cross-sectional area and insulation thickness. To calculate the allowable fill for a Wireway or gutter, you must first determine the cross-sectional area of all the conductors that will be installed in the Wireway or gutter. Then, you must use the dimensions of the conductor with the thickest insulation to calculate the allowable fill percentage. The allowable fill percentage is the maximum percentage of the Wireway or gutter's cross-sectional area that can be occupied by conductors. The NEC specifies different allowable fill percentages for different types of wireways and gutters. For example, the allowable fill percentage for a wireway with conductors number 4 American wire gauge or ALG or larger is 20%, while the allowable fill percentage for a wireway with conductors smaller than number 4 AWG is 40%. In addition to the fill requirements, the NEC also specifies other requirements for wireways and gutters, such as the minimum size of the wireway or gutter, the maximum distance between supports, and the grounding requirements. It's also important to understand the distinction between wireways and pull boxes. Wireways are continuous raceways used for housing and protecting conductors, while pull boxes are enclosures used to facilitate the pulling of conductors through long or complex raceway runs. NEC 314.28 provides specific requirements for sizing pull boxes, junction boxes, and handhole enclosures. These requirements are based on the size of the conductors and the number of raceways entering and exiting the box. The general rule is that the pull box must be sized to provide adequate space for the conductors to be pulled through without damaging the insulation. The size of the pull box is determined by the raceway size, the number of conductors, and the angle of the pull. For straight pulls, the minimum length of the pull box is 8 times the trade diameter of the largest raceway. For angle pulls, the minimum length of the pull box is 6 times the trade diameter of the largest raceway, plus the sum of the diameters of all other raceways entering the same side of the box. The depth of the pull box must be sufficient to provide adequate space for the conductors to bend without exceeding the minimum bending radius specified in the NEC. The width of the pull box must be sufficient to provide adequate working space for personnel to install and maintain the conductors. It is essential to consult the specific requirements in NEC 314.28 to ensure proper sizing of pull boxes for different configurations and conductor sizes. In the context of the original question, the gutter is not being used as a pull box, so it does not need to be sized according to NEC 314.28. However, if the gutter were being used as a pull box, then it would need to be sized according to the requirements of NEC 314.28. Let's delve deeper into the conductor sizes and their implications. The question mentioned number 500 well conductors. kc mil stands for 1000 circular mils, and it is a unit of area used to measure the cross-sectional area of conductors. A circular mil is the area of a circle with a diameter of 1 mil, where a mil is 1/1000th of an inch. Therefore, a 500 mil conductor has a cross-sectional area of 500,000 circular mils. The NEC specifies the allowable ampacities for different conductor sizes and insulation types. Ampacity is the current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The ampacity of a conductor depends on its size, insulation type, and the ambient temperature. The NEC provides tables that list the allowable ampacities for different conductor sizes and insulation types. For example, Table 310.13b16 in the NEC lists the allowable ampacities for conductors rated 600 volts or less, and Table 310.15b17 lists the allowable ampacities for conductors rated over 600 volts. When determining the ampacity of a conductor, it is important to consider the ambient temperature and any dilating factors that may apply. Dilating factors are used to reduce the allowable ampacity of a conductor when it is installed in conditions that are less than ideal, such as in a hot environment or in a conduit with other conductors. The NEC provides tables that list dilating factors for different conditions of use. In addition to ampacity, it is also important to consider the voltage drop when sizing conductors. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that the voltage drop in a branch circuit should not exceed 3% and that the voltage drop in a feeder should not exceed 5%. To calculate the voltage drop in a circuit, you need to know the length of the conductor, the current flowing through the conductor, and the resistance of the conductor. The resistance of a conductor depends on its size, material, and temperature. The NEC provides tables that list the resistance of different conductor sizes and materials. Now let's discuss the grounding conductor mentioned in the question. Grounding conductors are used to provide a path for fault current to flow back to the source in the event of a ground fault. A ground fault occurs when a live conductor comes into contact with a grounded surface, such as a metal enclosure. Grounding conductors are typically made of copper or aluminum and are sized according to the requirements of the NEC. The size of the grounding conductor depends on the size of the ungrounded conductors in the circuit. The NEC provides tables that list the minimum size of the grounding conductor for different sizes of ungrounded conductors. For example, Table 250.122 in the NEC lists the minimum size of equipment grounding conductors for different sizes of overcurrent protective devices. It is important to properly install and maintain grounding conductors to ensure the safety of electrical systems. Grounding conductors should be securely connected to ground at the service entrance and at each separately derived system. Grounding conductors should also be protected from physical damage. In summary, sizing electrical gutters, wireways, and pull boxes requires a thorough understanding of the NEC and its requirements. It is important to consider the conductor fill, the conductor insulation thickness, the ampacity of the conductors, the voltage drop, and the size of the grounding conductors. By following the requirements of the NEC, you can ensure the safety and reliability of electrical systems. Remember to always consult the latest edition of the NEC for the most up-to-date information and requirements. When selecting conductors for a particular application, several factors must be considered to ensure optimal performance and safety. These factors include the ampacity of the conductor, the voltage drop, the insulation type, the environmental conditions, and the mechanical strength. The ampacity of a conductor is the maximum current it can carry continuously without exceeding its temperature rating. The ampacity is determined by the conductor's size, material, and insulation type. The NEC provides tables that list the allowable ampacities for different conductor sizes and insulation types under various conditions. It is crucial to select a conductor with an ampacity that is sufficient for the intended load to prevent overheating and potential fire hazards. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that the voltage drop in a branch circuit should not exceed 3% and that the voltage drop in a feeder should not exceed 5%. To minimize voltage drop, select a conductor with a larger cross-sectional area or use a higher voltage level. The insulation type of a conductor is critical for protecting it from environmental factors and preventing electrical shock. Different insulation types are designed for different applications and environments. For example, THHN insulation is commonly used for dry locations, while THWN insulation is suitable for wet locations. The NEC specifies the allowable insulation types for different applications and environments. The environmental conditions in which a conductor is installed can significantly affect its performance and lifespan. Factors such as temperature, moisture, chemicals, and sunlight can degrade the insulation and reduce the ampacity of the conductor. It is essential to select a conductor that is suitable for the specific environmental conditions to ensure its longevity and reliability. The mechanical strength of a conductor is important for withstanding the stresses and strains that it may encounter during installation and operation. Conductors should be able to withstand bending, pulling, and vibration without breaking or becoming damaged. The NEC specifies the minimum mechanical strength requirements for different types of conductors. When installing conductors, it is crucial to follow the manufacturer's instructions and the requirements of the NEC. Proper installation techniques can prevent damage to the conductors and ensure their long-term performance and safety. Some common installation practices include using the correct tools, avoiding sharp bends, supporting the conductors properly, and terminating them securely. Regular inspection and maintenance of conductors are essential for detecting and addressing any potential problems before they lead to failures or hazards. Inspection should include checking for signs of damage, such as cracks, cuts, or abrasions in the insulation. Maintenance activities may include tightening connections, cleaning the conductors, and replacing damaged sections. By following these guidelines, you can select, install, and maintain conductors effectively to ensure the safe and reliable operation of electrical systems.